Good afternoon. My name is Tolga Tekin. It is my pleasure to present manufacturing aspects of data center transceivers. It is clear to all of us that in the current data age, the data stored and processed in data centers are growing rapidly. The demand in the applications, such as coming from social media, big data, health and wellness, security, or IoT, is defining the amount of data which is created. Just take a look to the predicted numbers. It is expected that we interact more than 4,000 times a day with IoT devices. 25% of the created data will be related to the real-time applications. And overall, the annual created data will reach 160 zettabytes soon. So the size of data centers is increasing quite significantly to respond the demand coming from the applications. The data center network could be segmented into three rather large groups: cloud computing, high performance computing, and classical telecom like enterprise networks. Regardless of those market segmentations, all of these are actually different versions of the same data center. The data center can be realized in this well-known spine architecture. A server is connected to the others with full mesh topology. Network composed by Ethernet switches is connecting the servers. This data center mainly growing by adding a new switch layer when it's running out of the capacity. The bandwidth demand grows exponentially inside the data center. More than 70% traffic stays inside. Between the switches is the optical connectivity the main focus. The switch capacity is also defining the layer hierarchy itself. In the past, in Foxtrot project, we have been developing optical interconnects between the racks, between the line cards, and between the chips. And in L3 matrix, our focus has been co-packaging of terabit switches, mainly disaggregation of the switch IOs into the optical domain. Different metrics can be applied to such a network infrastructure: volume, cost, complexity. In the lower layers, the volume is the highest, therefore is the cost also the lowest. If we move up, it's becoming complex. Active optical cables, then the domain of single mode optics in tier 2, and close to the edge of data center we see coherent optics. Here is the cost the highest. Due to the fact that we would like to have the highest capacity per fiber, here is the complexity also the highest. Where do you find photonic integrated circuits, especially silicon photonics, in that architecture? First products appeared where active optical cables were. Here we have high volume and low cost. Later we see the high end of the network. It is not due to the cost, it's rather due to the complexity. And now also in the middle tiers, the products are coming. On the right, we see the transceiver industry growth. The spacing between the line rates are getting shorter and shorter as we proceed in time. It is because of the very fast increase of the aggregation bandwidth of Ethernet switches. It is clear that transceiver data rate follows Ethernet switch port speed. On the left, we can see the actual correspondence, which is the SerDes speed. It is defining the port speed of the transceiver directly. In the moment, 12 terabit switches and 400G transceivers are on the market. The next steps will be 25, 50 terabit Ethernet switches, and also 800G transceivers respectively. Along with the clear demand on data center capacity, the Ethernet link speeds are growing. 400G ramped up already. In the next years, we will see 800G and 1.6 tera. Here, the standards and MSAs are already in the pipeline. For beyond 400G operations, we will be seeing a couple of new solutions with respect to the packaging. They might include COBA-like or any co-packaging-like solution in the housings. Transceiver market reaching critical mass to leverage cost saving of silicon photonics now. It is also reflected in this forecast. Silicon photonics growing faster in data centers compared to the other segments. Other segments would be also including 5G and beyond, so those will be potentially new segments where silicon photonics would grow also in the next decade. Now, looking at the metrics to test our data center transceivers, most important one is the cost. The hyperscale players do not care about the performance as long as the cost is low enough. There is constant pressure to reduce the cost. Industry-wide goal of $1 per gigabit per second is quite difficult to achieve, especially with single mode. The requirements are strict and driving the technology to identify lower costs in assembly and also in devices. Next demand is reducing the power, even though the contribution of optics is small in data center. But it is required since the allocated power for optics is limited. With increasing number of transceivers, it's becoming more critical. Reliability is the last important metric, especially for lasers and packaging technologies. So what is the wish list for next generation transceivers? So the key challenge is how we can take aspects from VLSI industry into this market. So those are integration density, high temperature operation, high channel count, mass manufacturability. Actually, silicon photonics and wafer scale CMOS processing in combination is quite promising. But there are too many sequential manufacturing steps between photonics electronics wafer fabrication and transceiver product finalization. So those should be taken care about. How we address those challenges, this wish list, we work on 300mm silicon photonics platform to provide the required density and high channel count and support the entire mass manufacturing processes. Then we combine it with the true silicon via processes in order to provide the compatibility with advanced silicon assembly techniques, and then combining in-plane and vertical couplers and also dense fan-outs for optical IOs, we do manage to have low loss and again high count optical IO, and then in the combination with high TRL laser assembly, where we rely on silicon bench and established assembly processes, we tight the entire alignment tolerances. That allows us actually to reduce the costs below $1 euro per gigabit per second between the racks and also below 10 cents inside the rack. Mustard is a collaborative approach reflecting the entire value chain from technology to systems, with the partners focusing on different aspects such as Leti on silicon photonics fabrication, Almai on laser EML fabrication, Team Photonics developing the optical fan-outs, Fraunhofer IZM we focus on through silicon via and assembly technologies, Bright Photonics developing dedicated PDKs, FireContact, the main focus automated assembly machines and equipments, Tektronix supporting with automated testing, Aristotle University in Thessaloniki with system tests, DAS Photonics providing sub-assembly, Mellanox NVIDIA is taking care on the intra-data center transceiver as a product owner, and respectively also in the inter-data center transceiver segment, ADVA is playing the role of the product owner. In order to optimize the cost, power, and reliability, it requires a dedicated design for high-volume manufacturing to enable passive or fully automated assembly steps. Further, it should be enabling the reduction of BOMs and also eliminating labor-intensive alignment steps. It's also required to support extended reach and high temperature with one single design, and even the next data rates should be enabled by using the same optical design. At the right, we see the transceiver designs for VCSEL-based, Eml-based, and silicon photonics-based transceivers. The optical packaging tasks and challenges are almost similar. So in the silicon photonics case, the alignment of DFB to the silicon photonics chip, the chip to the fiber, and for the transmit circuitry, for the receive circuitry, fiber to silicon photonics chip alignment. Those are the main features which we see also similar in the other ones. So the technology profited from keeping optical packaging tasks similar. So at the right hand side we see the developments 100G, 200G and 400G. Now 400G is taking almost the overhand in a couple of years, and then there will be estimated arrival of 800G transceivers. 800G is becoming interesting since the DSP will be kind of optimum in that case, with electrical and optical lane rates the same 100G. So it will mainly allow us to keep cost per gigabit in an optimum way, and that's why it can be expected that it will dominate the market soon. So the time gap between 400G and 800G will be significantly shorter compared to the ones between 10 and 40, 100 and 400G. So giving the simplicities and basing optical packaging tasks kept constant, it will allow us to go to 800G in a shorter term. So since we are focusing on silicon photonics-based transceivers, we have to understand the basic technologies to build such ones, such as laser sources, silicon photonics processing, pump form modulation, and also fiber coupling itself. All of those technologies are challenging by themselves. Now, going briefly through all of them. So at AMI, we are developing high-power DFB-based lasers relying on aluminum-free multi-quantum wells. It enables us an uncooled operation with low threshold current and high output power. It is compatible with buried heterostructure technology, and the new generation of those aluminum-free MQW lasers are reaching also good output powers at 75 degrees C. With respect to silicon photonics, we rely on LiTi technology. It advances in 300 mm, consisting of several building blocks, passive and actives. With respect to actives, you can count germanium photodiodes and also Mach-Zehnder modulators. With respect to photodiodes, the dark current is very low. Responsivity is about 0.7 amps per watt, and the bandwidth is at -2 volts above 35 gigahertz. With respect to modulators, it's Mach-Zehnder based. Vπ at -2 volts is about 1.5 volt per centimeter, and the losses are 7 dB per centimeter, and bandwidth at -6 dB, corresponding 25 gigahertz. The LiTi platform is actually a very ultra-low propagation loss platform. Some numbers of strip waveguides at 1300 with respect to the losses is 1.1 dB per centimeter. At 1550 it's about 0.7 dB per centimeter, and it allows a set operation above 25 gigahertz modulation. That silicon photonics platform we combine with TSV processes at IZM. Here we see a process flow, front and back side processes, and allowing actually a compatible design with CMOS assembly technologies over there. Further, we rely on specific couplers, WAFT-based one, in order to adapt pitch and mode. Itself is a glass-based waveguides with very uniform losses below 0.7 dB at the interfaces, and allowing us to arrange the dedicated pitch adaptations. Further, collecting all those in PDKs is becoming the main challenge if you would like to move towards 1.6 terabit per second, since we have to reflect the entire multiple technologies coming from silicon photonics 3.5 and glasses, and including also assembly design rules towards multiple IP use blocks, combining in such a way to enable a complex routing and also a scalable design with dedicated interfaces kept at the right positions. By doing so, we enable a new generation assembly and coupling and packaging approach, keeping the design boundaries similar for all those dedicated portions. Further, with respect to mass manufacturing, it's becoming mandatory also to have automated die testing platforms, which has been developed in Thessaloniki, consisting of optical and RF testing in one platform. So considering the boundaries for all the technology processes and testing, and keeping also the design for optical assembly steps similar, it's allowing us to scale up the data rate for TOSA from 400G to 800G. As we can see, all the belonging parts are similar. We do rely on a silicon bench and then a laser array attached on that, further dedicated lens array and isolator, and the coupling optics to couple the laser light to the silicon photonics is there. After the silicon photonics, we do have again a lens array and fiber array. So the most critical part is sure the laser to chip coupling, where we only rely at that point we rely on active coupling of active assembly. All the other assembly steps are based on passive assembly. So the design is done in such a way that we keep the main assembly steps constant, only the dimensions and so on changing, and by doing so it's becoming a standard approach towards scaling up the TOSA module. With respect to ROSA, it is similar, again relying on silicon photonics, 4-channel, 8-channel in that dedicated case based on WDM. There we see the AWGs over there, keeping the assembly steps similar. It allows us to scale up again from 400G to 800G. Here at the left bottom, we do see the dedicated lens array coupling to the PIC itself. So as shown in TOSA and ROSA, the design allows us scaling in the data rate by relying on unchanged assembly steps, where most of them are passive. By doing so, we are able to create a generic assembly flow and dedicated fully automated assembly line. So we have to keep in mind the final cost is most likely defined by the machine cost, the footprint and clean room area itself. And in order, if we try to enable a higher throughput for all the assembly steps, we will be managing also the lowest cost. Here in the bottom, it's a possible layout for mass manufacturing assembly line of transceivers is depicted, consisting of feeding in and out systems and with modular cells consisting of passive assembly, active assembly features. So following the automated assembly, the next step is sure the automated testing. Here we rely on machine learning based automated testing equipments, by doing so reaching to the next generation products for our product. So 600 gigabit per second capacity with coherent transceivers is one of our demonstrators, where we'll rely again the basic building blocks which have been developed based on silicon photonics and so on, all the assembly technologies bringing together automated, assembled and automated tested. So in the other hand, this automated assembly, testing and dedicated design allows us to address QSFP-DD based format 400G and beyond, namely 800G aggregate bit rates addressed. Moving towards 1.6 terabit per second where as mentioned, the packaging boundaries are not clarified yet. That will be sure kind of onboard module to deliver the 1.6 terabit aggregation. My start project initiated around the question how to enable mass manufacturing for datacom photonic products. So what we have identified over there, a clear path through automated manufacturing, where we mainly consider the building blocks, our know-how from 400G beyond 1.6 terabit per second in the data rates. So by doing so, we could manage a competitive cost according to the interconnection distances also. It relies actually on a proven design of the dedicated building blocks, chip manufacturing, including photonic electronics, which is scalable, the integration and packaging concepts, which is automated testing, and also demonstration in a real environment by support the standardization actions. It's mainly allowing us a peak-based optical transceiver with transfer rates above 1.1 terabit per second, enabling massive deployment in data center environment by keeping the costs below $1 or euro per gigabit per second between the racks and below 10 cents per gigabit per second inside the rack. It requires actually a dedicated ecosystem and improved cross-fertilization between photonics and other technology areas, as I was reflecting in my presentation.